All right, let's look at polar curves in AP Calculus, specifically AP Calculus BC, and we're going to look at areas contained by polar curves in this lesson. And if you want to print the guided notes sheet that I give my students, you can go to this bit.ly link here if you'd like to have the problems written in front of you. And I'm going to start by showing you where the formula for the area contained by polar curve comes from. I think there's some benefit to seeing that. And so we're going to start by remembering that the area of the sector of a circle, so if you have a circle and you want to know the area of just a piece of it, if you know what the central angle is, the area is 1/2 r squared theta. And so that would give you just the area of that one little sector of the circle. And we're going to use that thought process to figure out what the overall area contained by this polar curve is. And I'm going to do that by dividing this region up into a whole bunch of little sectors, kind of like a Riemann sum type approach with polar curves, except we measure everything in polar curves back to the x-axis. So I'm going to divide this, I think for simplicity, I'm going to divide this into 3 little sectors. So I'm going to have one right here, and I don't know what that angle is. I'm going to call that angle delta theta. And then I'm going to continue dividing this region up. I'm going to go until I get to the curve, and then I'm going to create another wedge right here, and we'll call that wedge another delta theta. Same angle, we're going to use the same angle each time. And then my last little wedge to get this last piece is going to be right here. And I have divided this up into 3 subdivisions, and we're trying to find the sum of these areas. So we're looking at all of these areas right here, and we're going to add up these areas. Well, we're going to use that formula, 1/2 r squared theta, and each one of those sectors, I'm going to be a little bit lazy with my notation here, this is not going to be a formal proof, but each one of those areas is 1/2 r, and the r changes, so really I should do like r sub 1, and this one is r sub 2, and this will be r sub 3, or little r sub 3. So it's r sub n squared times the central angle, which will be delta theta. And we're going to add those together. So I'm going to take the sum of each of those, and here's where I'm going to be a little bit lazy. It's the sum of 1/2 r squared delta theta. And right now I only have 3, but if I want the area to be more accurate, I would use maybe 6 subdivisions, or 20, or a billion. And the more you take, the more accurate this becomes. And if you take an infinite number of subdivisions, if that delta theta gets infinitely small, we represent the sum of those areas as the sum, and this is an elongated capital S for the sum. That's a Greek letter S, now it's an English letter S, of 1/2 r squared. And the delta theta will get infinitely small, as represented by a d theta. And then we will indicate that we are doing these starting with an angle of theta equals A, finishing with an angle of theta equals B, and that is the formula that we are going to use for the area of a polar curve. So not a perfect proof, but it's a little bit of an explanation that might help you remember the formula for the area of a polar curve. And so let's look at a few examples of putting this into use. And we are only going to set these up because they typically produce some pretty difficult antiderivatives. I'm more interested in just showing you how to get them set up. I will punch these in a calculator to give you a numeric answer in the end. But let's start by setting these up. And I'm not going to go into great details about how to graph these polar curves. If you need a lesson on how to graph polar curves so you can see the region, then I'm sure there are a billion YouTube videos showing that. I may even have one, I don't know if I do. But I'm going to graph this really quickly, and then I'll talk very quickly about how I got the graph, and then we'll find the area described. All right, so here's my graph. I'm going to quickly explain how I did this. When I see a number plus or minus a number and then sine or cosine of theta, I know it's going to be one of these 4 shapes. See, there are 3 shapes. It'll either be a cardioid, a limicon, or a limicon with a loop, or limicon. I'm not sure if that's a hard or a soft C. I'm going to brush up on my French. But I know it's going to be one of those 3, and they can be oriented and rotated 90 degrees depending on whether it's sine or cosine, or whether this is a plus or a minus. And to figure out what it is, I just plug in my sexy 90-degree angles, 0 pi over 2, pi, 3 pi over 2, 2 pi. I find out what the corresponding r is, and once I plot those points, I can then see what the shape is. And so there's how I graphed that one. And we are interested in the first quadrant region, and as I expected, the first quadrant region is enclosed between the angles of 0. That's where we start, and we finish at theta equals pi over 2. Now, don't assume that the first quadrant is always 0 to pi over 2 in a polar curve, because I have seen situations, and it depends on how the curve is written. It could be that you escape the first quadrant when the theta is not pi over 2. So always verify the limits of integration. And now that I have those limits of integration, this region is contained by my angle starting at theta, going all the way up to pi over 2. That's the entire region that I'm looking for. And the formula is 1/2 antiderivative angle to angle, theta to pi over 2, of r squared. So we need to grab all of that, 2 plus 2 sine theta, squared d theta, and that's it. That's the new stuff. That is the area of the first quadrant region. And then, like I said, these typically are fairly ugly or drawn out antiderivatives if done by hand. So I'm going to throw that in a calculator very quickly just so we can have an answer, and then we'll move on to the next example. And there's my answer, and I'm using the TI Nspire to get that answer. So let's look at another one here. The area inside one loop of this, and this is a polar curve. They're all polar. This is a Rose graph, and let's see, if the coefficient of theta is odd, that tells you how many petals there are. So there are 3 petals. They are 4 units long. The units long. That was what is that? 4 units long. There we go. And then what I do next is I do something called finding the long r. What is the longest that the petals can be? And that's going to be when sine theta is at its maximum. I want to know when sine of 3 theta is equal to 1. And so I'm going to find that long r. What is the largest r? What is the longest, the point where the petal is at its longest? And so I need sine of 3 theta to equal 1. Sine is equal to 1 when you are taking the sine of pi over 2 and certain multiples of that. And that happens when theta is pi over 6. And so now I can get a fairly accurate graph. And I want my first petal to be going in the pi over 6 direction. And it's going to be 4 units long. So I'll go out 1, 2, 3, 4. We're going to go from 0 all the way out to there, and then it's going to come back in. Pi over 6. And then all the petals are going to be divided evenly. So here's where I'm going to actually think in terms of degrees. If there are 3 petals, 360 degrees divided by 3 is 120 degrees. This is 30 degrees. And so if I move 120 degrees more, I'm going to be in the 150 degree angle. Yeah. So I'm going to go 150. And then the next one is going to go down at 270. So not very pretty, but hey, there's my polar curve. And we want the area inside only a single petal. Only a single petal. So I only want that. And there are a couple of ways you could do this. But probably the easiest way, since we're not solving this by hand or anything, would be to find out what is the angle where I'm starting, and we're going to come out, and I need to know when we finish, and we finish back here at a certain angle, and that would be when sine of 3 theta is equal to 0. If you're on the pole, you are 0 units away, so I'm going to find that spot by determining when sine of 3 theta equals 0. And sine is equal to 0 when the angle is 0, pi, 2 pi, and so on. And if you divide that by 3, that happens when at the angles of 0, pi over 3, 2 pi over 3, etc. And 0 and pi over 3 are going to be these first 2. So now I'll have my angles that contain that very first loop, and the area inside that first loop is going to be 1/2 antiderivative 0 to pi over 3 of your r which is the quantity 4 sine 3 theta, all squared. And there's your setup. Now, this could be a multiple choice question where they give you the setup as the options and then not the actual answer. They give you the setup. And it is possible to take advantage of symmetry here, because I actually could have found the area only to that angle of pi over 6 and doubled that. Because if I go from 0 to pi over 6, that's only half of the pedal. So I could do twice the area from 0 to pi over 6. R doesn't change, so it's still 4 sine 3 theta squared. And then obviously 2 times 1/2 is 1, so we could divide those away. And they may give you the answer of choice like that. So sometimes it will take advantage of the symmetry. I'm going to punch that in the calculator, see what the answer is, and then we'll move on to the next example. All right, there we go. I got 4 pi over 3. And just to double check myself, I did punch both of the integrals in my calculator. And so there's from 0 to pi over 6, and then down here you see half of 0 to pi over 3, and we do get the same answer both times. So I did that just to confirm that I didn't make any mistakes. Let's see, I think I have 2 more. Yes, 2 more. All right, so let's look at this one. The area common to both r equals 2 and r equals 3 plus 2 cosine theta. Ooh, let's see. Let me graph those and see what's going on with this one. All right, so here's the graph. So we have a limison, a dimpled one. I guess there's a dimple. I didn't investigate it enough to figure out if there's a dimple, but that's a good enough graph. We want the area common to both of those. By the way, r equals 2 just means your distance from the center, from the pole, is 2 units, which describes a circle. All points are 2 units from the center. And the area or the region that is common to both is all of this. All of this. And we got to find that area. There are a couple of ways you can do this, but I think the easiest way, I'm going to take advantage of symmetry, because I can tell that what's above the x-axis is the same as what's below the x-axis. If I can get only the top part, whoops, redo, there. If I can get only the top part, I can double that. And then that'll give me the whole area. But we have a little bit of a situation here, because we have 2 boundaries here. And remember, we generate our graph by rotating around the around the pole from the positive x-axis. And so we start here. And for this first part of the region, think of it like a Doppler radar generating clouds that sweeps around. But as we sweep that angle around, this first part right now, all of this part is contained only by the circle. The limison's not part of it there. And then once I pass this angle, now we're contained only by the limison. And so we're going to have to break this up. And I need to know, what is that angle where the 2 graphs intersect? And we get that angle by setting the 2 equations equal to each other. When does 3 plus 2 cosine theta equal to, that's when cosine of theta is negative 1/2. And that's going to happen at the angle of 5 pi over 6. And it happens again in the third quadrant at 7 pi over 6. But I'm only going to get the top half, and I'm going to double that. So while that is true, I'm not going to use the 7 pi over 6. I'm only going to use the 5 pi over 6. And I'm noticing that from 0 all the way to 5 pi over 6, we are only looking at the area contained by the circle. And there are a couple of ways to do that, but I'm going to do this. I'm going to say that this overall area is going to be the area inside from 0 to pi over 6, 5 pi over 6 of only the circle. That's 2 squared d theta. Then I'm going to do the area from 5 pi over 6. I'm going to add to that the area from 5 pi over 6. And from 5 pi over 6 till pi, we're contained by the blue graph, the limison. And that's the equation, 3 plus 2 cosine theta squared d theta. And then keep in mind, I only found half the area. Now I need to put all of that in big honking parentheses. and double it because I only found half the area, and that would be a good setup to get the area common to both of those graphs. You do have the option, because this first part it's contained by the circle, that's only you can actually use geometry using the formula for the sector of a circle, which I showed you a long time ago right here. So if you want to use just like half r squared theta, you can do that for the red graph because it's a circle. I prefer just to stick with the integral notation because that's kind of where my brain is right now. So let's see, so there's that one, and I'll punch that in the calculator really quick. All right, so there's my answer for that one. Kind of ugly. I think I punched that in correctly. It looks correct. I decided to distribute my 2 to get rid of the 1/2, and I went ahead and did 2 squared is 4 because I'm really smart that way. Let's see, onwards to the last one, number 4. The area that is inside r equals 4 sine theta and outside the other one. I'm going to graph that real quick, and we'll talk about how we can divide this up and see what we have. Okay, so here's what our graphs look like. So we have 4 sine theta is a circle that goes through the origin and the y-axis at 4. This one ended up being a limicon with a loop, and just so you know, when you get a limicon with a loop, what you'll end up doing when you plot the 4 sexy points, I had a point at 1, 0, 0, 3, negative 1, 0, and 0, 1, and when I have 2 points on the same side of the origin like that, that closer point is the tip of the loop, and it does go through the pole or the origin, and looks like that. So here's our region, or there are graphs, and we want the region inside the circle but outside the loopy limicon. And so I'm going to highlight that. We're inside the circle, so we're looking at this piece right here. Looks kind of like a moon. Looks kind of like a moon. This is not drawn perfectly because it should be symmetric on both sides, but kind of like the last problem, we're going to need these intersections. I need to know when do these cross each other, and we'll figure that out by again setting these graphs equal to each other. And so when you set those equal, we have 4 sine theta is equal to 1 plus 2 sine theta, subtract the 2 sine theta, that's 2 sine theta equals 1, sine theta equals 1/2, which is happening at pi over 6 and 5 pi over 6. And again, if you want to, you can actually take advantage of symmetry, and you could go 0 to pi over 2, or I'm sorry, you can go up to pi over 2 and double that. So we're definitely going to start at pi over 6. Now this time the area is between the 2 curves. That's a different setup than what we had here, where we were only using one curve for the first part and the second curve for the second part. Here, they're both boundaries at those angles that we're going to be concerned about. And what we'll do is we'll find the area, essentially, all of the area inside the circle, then we'll find the area inside the limicon and subtract it away. Okay? So we're going to do the area inside the circle, which would be the area from, and I guess I'll go pi over 6 all the way to 5 pi over 6. Pi over 6 to 5 pi over 6. Don't forget the 1/2. And that's of the red graph. So I'm getting the whole region inside the circle. So that's 4 sine theta, all squared. And like I said, that gets me all of this. Highlighter, there he is. That gets me all of this, and then we need to take away everything that is inside the limicon. So I need to now subtract all of this, which would be the area from pi over 6 to 5 pi over 6 of 1 plus 2 sine theta squared d theta, and there we have it. Now that can be combined into a single antiderivative because we have the same limits of integration, the same coefficient of 1/2. So it could do half of the integral of 4 sine theta squared minus 1 plus 2 sine theta squared. You can separate it like this, doesn't matter. But this is now pushing a 20-minute video, and that's kind of where I want the maximum that I want. So I'm going to punch this in the calculator really quick, see the answer, and we'll call it quits. All right, there we go. So I did decide to put this in the calculator as a single antiderivative. And something I forgot to mention earlier, I'm using x in the calculator. It doesn't matter if you want to use x's or thetas. And there is the answer for this one. And again, like I said, if you wanted to, you could have done the area from pi over 6 to pi over 2, get that first quadrant portion, and then double that to get the rest of it. And that's something to look for in multiple choice questions. So that's it. I'm done. This video is too long.